I'm Bhavidhir V. Bharadwaj. Welcome to episode 30 of Genesis of Tomorrow. The following is a conversation about many body quantum physics, the arrow of time, unitary dynamics and equilibration, quantum chaos, and more with Dr. Jonathon Riddell, a physicist and researcher at the University of Birmingham. Also, folks, if you are interested in such deep tech or deep science conversations and are able to derive even the slightest bit of value from the show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. Okay, we are rolling now. First of all, once again, welcome on the show, Dr. Riddle. It
Yep.
is a pleasure to have you here. And before we move forward into talking about all these different aspects in depth, it would be really, really good if you can give the people who will be turning in a brief gist about what statistical mechanics is and its related principles and how it overall comes up from the underlying quantum dynamics of many body physics.
Yeah, so that's a huge question. So statistical mechanics is a really interesting subject that I've dedicated a big chunk of my life to. So statistical mechanics is the way that is the framework in physics that we use to describe systems of many particles. So when you go through a physics undergrad, typically the storyline is that you learn Newton's laws. Maybe you learn a fancier version of classical mechanics like Lagrangian mechanics or Hamiltonian mechanics, and then you move on to quantum mechanics and you learn Schrodinger's equation. Now, the interesting thing about all these topics is typically what you're doing is you're describing few particles, or you're describing very like idealized things. Like in electromagnetism, you might study a rod of infinite length, right? And then and then you're describing the electrical field, very far away from this rod, and maybe you're sort of starting to get this while you're going through these topics, maybe you're starting to get this sense that. When physicists try to make analytical progress and we try to use the equations of physics, it's actually really difficult to get analytical solutions from the equations of physics, right? It's easy. We've made a lot of progress. Like humanity's made a lot of progress writing down, Maxwell's equations, Schrodinger equation, all of these beautiful, beautiful equations that you learn in physics. The real bottleneck in science is actually using the equations and solving them. And so, like you might have heard of the three body problem. When you have two bodies, I can always write down the solution to the equations. If there's two bodies interacting with each other, the moment you have three bodies, you start to get into situations that are called non-integrable situations, where I can't actually write down the solutions in a clean way unless I have special cases. So then, what do we do? What do we do when we get when we get this problem? Well, one thing that you can do is you can turn to statistical mechanics. And instead of describing what the particles are actually doing at every point in space and every point in time in a very precise way, what you do is you build statistical descriptions of what the particles are doing. And so statistical mechanics underpins, for example, our understanding of thermodynamics. People love it sort of takes our microscopic description of physical systems and allows us to build more of a macroscopic picture, which gives you the in between step between the laws of motion and thermodynamics, and that's specifically statistical mechanics. And it's sort of for many people it's an unsatisfying description, because when you take typically in courses, and the way this is presented to people is that you take the laws of motion, and these are like laws of nature, right? They might be approximate laws of nature, but at least for the regime that you care about, when I'm doing Newton's laws, I'm not describing things that are going too fast. And when I'm doing Schrodinger's equation, I'm also not doing things that are going too fast or whatever. And so there's like a degree of applicability, but they're laws of nature. And then when I the first your first exposure to thermodynamics, like that's the setting that you're thinking about physics in, right? Thermodynamics, like they're all it's thermodynamics is also appears to be making fundamental claims about the way the universe works, right? And then it's like, okay, so how do I get from point A to point B? How do I get how do I get from the laws of motion to thermodynamics? And the answer is well, you make these weird statistical arguments. They're not weird. I mean, there's good intuitive reasons for why we use them. But basically, what happens is you go from very very like universal statements about physics to a statistical argument, and then all of a sudden you come out on the other side and you have thermodynamics, and you realize that these thermodynamic statements that um, you probably processed as being truth statements about the universe, they're really statements that are true on average, and sometimes it's a little murky where the origin of these statements come from the microscopic description.
As an overarching matter, and a description from you, how exactly for somebody who is not very much aware or versed with how it happens, macroscopic phenomena originates or translates from the microscopic quantum interactions or the dynamics between these small particles.
Yeah, so I can give you two stories. I'll give you the old story and I'll give you the new story. Okay. So there's been a lot of progress in the last like 20, 30 years on our description, but I'm going to give you the classical story because the classical story really fits into the narrative that I just described in the sense of you're making these potentially unsatisfying connections, right? So the idea is the following: suppose I have a bunch of particles in a box, and they're interacting in various ways, right? They have a gravitational field. Typically, this isn't super relevant. And they're bumping off of each other, and there's lots of things. There's lots of things going on. So many things going on that it is impractical to attempt to track even the initial conditions of the system um, of particles. Now, basically, what we care about then when with this description, with this difficulty, we decide to do some type of statistical description. Now, what one might say then is that what actually matters is the type of configurations the system is allowed to be in. Okay, so the system will have conserved properties if they're particles in a box, or if they're spins on a lattice. What they're going to have is they're going to have fixed properties, and one of those properties, in an example you can construct, is they're going to conserve their energy. Now that's a microcanonical, that's a microscopic description, right? So the particles will always have a fixed energy, and so if they're all interacting and bouncing around everywhere, or the spins are flipping, or whatever system we're talking about, basically the idea is that no matter how the system changes, something that won't change is the energy. Um, and then from there, there's a couple ways to get to statistical mechanics. So one way to get to statistical mechanics is just to say, okay, well, I am ignorant of what the system is doing. And so what I'm going to say is that every configuration that is possible, I will just make those equal probable, right? So if I have 100 configurations, the probability that the system will be in one configuration is 1/100, right? So it's a uniform distribution. And that's what we call the microcanonical ensemble, from a technical perspective. Another a more rigorous way to say that is that I'm going to come at this from the perspective of ignorance. And it's sort of a deeper concept, but it's the one that I embrace because it's called subjective statistical mechanics. You know, statistical mechanics has interpretation issues just like quantum mechanics, like what's actually making these things work. And from an intuitive perspective, I think the answer is a lot clearer, and that is that the a lot of the configurations that are allowed at a specific energy, a lot of them look extremely similar. So when you do statistics on those, the mean value of the things that you're tracking are highly concentrated. But yeah, so to make the equal probable idea more rigorous, you can look at something like Jane's principle, and Jane's principle basically is a more formal statement from what I just said, and it's that at equilibrium, a system of particles will tend to a distribution on their microstates that maximizes entropy. And so the concept of entropy is inserted into your description. But here, entropy specifically is not particularly a physical quantity from this description. It is a function that's trying to tell you something interesting about the physical system. A more physical and more microscopic description actually is that okay, so take those on take the statistics that you expect and that work, right? And now what we can say is something along the lines of the ergodic hypothesis. I feel like I'm going very fast, so feel free to stop me if I'm not being very clear. But an alternative to throwing up our hands and saying I'm ignorant, I have no idea what's going on, I'm just going to do statistics. An alternative to that is something called the ergodic hypothesis, and the ergodic hypothesis basically says that um, all those statistics that you're doing that are independent of time. Okay. Now, actually watch one of these systems in time, or watch a property of the system in time, and then take the time average. So, what is this? What is this particle doing on average? What is its kinetic energy on average, or what's its spin orientation? Um, and the ergodic hypothesis makes the claim that that time average will be equivalent to the statistical average that you took, like, of the system. So it's comparing. It's basically saying that the ensemble average of many configurations of the system will be equivalent to one system's properties on average. And so that's the classical story. Okay, and I think the ergodic hypothesis is from a microscopic perspective is the most satisfying in some sense. I The problem is that the time scales at which you have to average are extraordinarily long. And the thing is I think we can both agree that when you're boiling water, or when you touch your desk, like that is very clearly well described by things like temperature and like other thermodynamic properties, right? So it's kind of unsatisfying. um, and so I tend to favor more the subjective interpretation of I'm just modeling here, I'm going to maximize the entropy, and I'm going to use the description, like the probability description that comes out of that algorithm. um, Now, the more modern approach now is significantly more satisfying, but it's also very new. So in the 1990s, people were asking the question, okay, so if I start a quantum system in a pure state, okay, so we need a little bit of quantum mechanics for this description. If I start a quantum system in a pure state um, is yeah, I don't know how to introduce this in a very quick manner, but basically in quantum mechanics you have pure states and you have mixed states. The statistics or the ensembles of statistical mechanics are given by mixed states, and basically they're mixtures of pure states. Okay. Now, pure states are typically like if I have a material and it's in its ground state, that state is always a pure state. Or the states that we evolve on quantum computers are pure states. You get mixed states from like noise from the environment, basically, and other things. So they're probability mixtures of the state of the system. And so if I was to take a closed quantum system, it's not interacting with the environment, and I was to prepare that system in some type of pure state. The question is how could statistical mechanics possibly evolve from that description? And the thing and the thing is that unitary dynamics. So the system is a closed quantum system. So the evolution in time of that system will be unitary. Now, unitary dynamics cannot make a pure state into a mixed state. Okay, so right away you're in trouble because the pure state dynamics is never going to globally look like anything from statistical mechanics. So how could statistical mechanics possibly emerge? Now, the interesting thing is that entanglement, right? So if I have a global pure state, um, dynamics typically of these closed systems typically entangle its constituents, right? So if I have a bunch of spins or qubits, as I evolve a system in time, all of the qubits will become more and more entangled. And this is kind of like a generic property of the Hamiltonians in the systems that you study in physics. And it turns out that when you then try to create a description of a subsystem of the system, right? So I cut my system into two, and now I have my system A and my system B. If I then only look at and try to quantify the statistics of system A, well, A is entangled with B, and it's sort of like a natural consequence. A is now a mixed state, so A could look like the statistics of statistical mechanics. And it turns out that this is precisely what we find for sufficiently. This is a very this is a weird statement to make because we don't know exactly how to make it yet. Is that for sufficiently generic Hamiltonians or quantum systems, um, the global system will thermalize its subsystems. So you take a pure state and it is globally not thermal. And by thermal, I mean it's not described by statistical mechanics. I do my time evolution, still globally does not look like statistical mechanics. But if I look at the subsystem looks thermal, or it looks like it gives statistics that you would find from statistical mechanics. And the one of the ways to explain this that hasn't been proved, but it is sort of like the dominant idea in the community, is it's called the eigenstate thermalization hypothesis. And anyone who knows me just probably smirked because I talk about this hypothesis quite a bit. I have several videos about it on my YouTube channel. Um, and my PhD thesis, it was a central theme in my PhD thesis. Now, the eigenstate thermalization hypothesis goes a step further. Okay, so when I want to solve, and I apologize if this is getting a little bit too technical, if I want to solve, like when I'm going to sit down and I'm going to write down the dynamics of a quantum system, what I want to do is I want to describe my state in what's called the energy eigenbasis of the Hamiltonian. So I want to solve the Hamiltonian's equations for all of its energies. So energies are quantized. So there's like if I have a qubit system and I have L qubits, then there's going to be 2 to the L energies that describe it. And along with those energies are going to come basically vectors. And to describe the dynamics of the system, it's very easy to describe the dynamics if I cast the dynamics in terms of this vector basis. Basically, it's just like it's a thing that's relevant for basically these are the fixed points of the Hamiltonian energy. They're equilibrium states on their own, but they're pure states. And the idea is that if you take globally a statistical description of the system from statistical mechanics, and then you look locally, and then you also take an eigenstate from the Hamiltonian that's at the same energy as your statistical description, right? Because we have fixed energy, it's a closed system. And then I also look at the same subsystem. The idea is that they're equivalent. So in some sense, the statement of statistical mechanics is trivial, because if I'm going to take a uniform average of energies, and I'm going to say, like, if the system can be in this configuration, I'm going to equally weight all of those different configurations. That, from a quantum mechanical perspective, that statement is almost trivial in the sense that all of those configurations already look like the statistical mixture on their own. So the statistical mixture is redundant in some sense. You only need one configuration of the system at fixed energy to find the correct description. And so this is the eigenstate thermalization hypothesis. There is like, let's say, loads of numerical evidence. There's a push that is very hard in the long term, to try and prove it. And we can go into why that is. It's like a very big. It's basically the same problem that we talked about at the beginning, in the sense of, if I have many particles or many things interacting, I can't do anything analytically. So how am I possibly supposed to prove a generic statement about systems like this that should be true for many different types of systems that already have this property that I can't solve them, right? So I'm not super optimistic. They're about us proving this, but this is our basically our best description um, of sort of the emergence of statistical mechanics from quantum mechanics. Now, if we go back to the ergodic hypothesis, the interesting thing about I'm going to call it ETH for now on, eigenstate thermalization hypothesis. The interesting thing about ETH is it doesn't need time averages. So if you look at the system, right? I mean, you have the whole quantum mechanical problem of, if you have to take the measurement, so maybe you have to do this multiple times and do your own average. But the idea is that the quantum mechanical average is equivalent to the statistical mechanical average on its own at fixed time. So you don't have to take time averages. It's just that is the true property of the system when you look at it. So it resolves at least the ergodic hypothesis issue that you can make about it. From a quantum mechanical perspective, you resolve this. Now, the next thing, though, is you still look at this sort of like circular dependency and the issue of, okay, so how did I know which statistical distributions to actually check the eigenstates against, like the actual configurations against? Well, I mean, you can go back to Jane's principle, and like sort of this completes your description, right? So the quantum mechanical systems actually have the property that on their subsystems they maximize what's called entanglement entropy. So it's the same entropy that you would use to calculate entropy. So eigenstate thermalization gives you that. The subsystems get what are called volume law entangled, and this gives their entropy, basically. And then you ask yourself, well, what quantum mechanics gives me this? What distributions maximize entropy? And the answer is that the ensembles from, or the statistical descriptions from statistical mechanics, they maximize entropy. So this sort of completes the story. And the remaining open questions is like, is it humanly possible to make some type of very generic proof that systems should satisfy ETH? And that's a big open question. And right now, the community has loads of evidence that, there's lots of caveats that would need to go into this type of proof, but we don't have a definitive proof right now.
Mhm. Exploring the this puzzle of equilibrium a little bit more. Why do these quantum systems, which are governed by unitary dynamics, or okay, let's take it a little bit in a step by step manner. What does unitary actually pertain to in this regard, in this context?
Unitary is basically a demand of quantum mechanics in the sense that when you describe a state of the system in quantum mechanics, what you're really doing is um, there's sort of like classical probability and there's sort of like quantum probability where you have to where you have to step back, and instead of talking about probabilities, you're talking about probability amplitudes. But what a quantum state really is it's a statistical description of what the system is doing. Now, that might have some naysayers from different interpretations of quantum mechanics or whatever, but that's essentially from a practical perspective, that's what a quantum state is doing. And so what unitary dynamics basically says is that if I'm going to evolve the state, um, the total probability of all possible outcomes has to be one, right? From a mathematical perspective, what that means is that if I'm describing the state of the system as a vector, that vector has to be normalized. And so unitary dynamics, it sounds like a very, very fancy word, and it is, but basically the idea is that um, uh, is that as I time evolve the system, I have to conserve probability. And so unitary matrices are generically matrices that conserve this property. So if you look at, for example, quantum computers, all of the gates in the quantum computer, all of those gates are unitary gates. So they're described by unitary matrices. And that's basically it. And it has this conservation again of pure state descriptions versus mixed state descriptions, and it has a bunch of you know like other things. Like I guess a really interesting aspect of unitary dynamics is not only does it make it strange to initially ask the question, why is statistical mechanics true, it also throws a wrench in why how a system could possibly be chaotic in the quantum sense. So um, okay, so in classical mechanics, one thing that the listeners can look up very easily is something called a Lyapunov exponent. And basically, the idea is you sort of have this like butterfly effect in classical physics when you have a chaotic system, right? You start two systems that are that are very, very similar, but they're a little different, right? In a classical setting, when you let those systems evolve, what happens is their trajectories through space and whatever through phase space, basically they exponentially diverge, and that exponential divergence is quantified with what's called a Lyapunov exponent. Now the thing is that if you then try to go back to quantum mechanics that has unitary dynamics, and you take a state, right, which is a probability distribution, and you take another state and you make them slightly different because of unitary dynamics. They're the distance that they are between each other, or sort of like one thing that you can do is like their fidelity in time, which tells you how different the states are, right? Um, it is like that's a constant in time that doesn't change. And so you don't get this Lyapunov exponent description per se right away in quantum physics. You need to go a little bit farther, and I would say that so back in the I guess the story is actually really interesting and very strange because people often ask me, what is quantum chaos, because people make the point of saying not just chaos, it's quantum chaos. And so back in, I believe it was the 80s, Wigner was studying atoms, and he was trying to specifically understand the spectrum of atoms, basically the energies of the atoms. And basically, what he found was something extremely strange. That the energies are well described, or statistics of the energies are well described again by basically looking at random matrices. Okay, so take a matrix that has for example Hamiltonians in physics always need to give you they need to give you energies that are real, right? And this is a special property. So these properties they have to be, if it's a matrix, it has to give you, it has to have a property that's called it has to be Hermitian basically. And if you take a random matrix that has the same property, right? Um, and then you get the energies of both your physical system and your random matrix. Um, Basically, what happens is that the statistics on the energies are equal, right? So one thing that you could take, one thing you could think about is, energies are, discrete and quantized. So you could order all of your energies from lowest to biggest, and then you could look at the gaps between the energies, right? Very strangely, this is given by what's called the Wigner surmise. It's like a Wigner Dyson distribution on the energy gaps. And so this type of equivalence between a random matrix and a physical system, it turns out that this is true in, for example, if I have a classically chaotic system, right? It has this Lyapunov, um, exponential divergence from similar initial conditions. If I quantize that Hamiltonian, then then, then that Hamiltonian that would now evolve with a system that would evolve with unitary dynamics, it has this property with random matrix theory, and that's what we call quantum chaos. It's really a property on the energies, and you can then start to look at systems that don't have a classical analog, right? So you didn't get the Hamiltonian, or you didn't get the system description from a originally a classical description, and then quantizing it to make it quantum. You can then look at things like qubit systems or magnetic systems that are fundamentally described by, spin degrees of freedom that don't have a classical analog, and then you go look at their statistics on their spectrum, and again, it looks like these weird distributions from random matrix theory. So when you're a quantum many body physicist, you essentially can't escape these strange, basically statistical descriptions of reality, because the way that matter organizes itself is is like it just matches it. It's just well described by these different distributions. Like the way matter organizes itself is very sort of, there are edge cases, and if you want to talk about that, we can talk about edge cases that violate these descriptions. But if you were to sit down and write down a physical system, odds are that they would satisfy these weird statistical descriptions, and that's because, like, on average, systems just sort of like their properties concentrate around these descriptions like very tightly, and this is like very much an open question um, in physics, and again, it comes back, the fact that this is an open question, but it's such a fascinating observation, is because the moment that you get three bodies in a system that are interacting with each other, we can't make analytical progress. Um, Interestingly, though, there is one example where we can make analytical progress, and I'll explain that. I'll explain that briefly. For so when I entered graduate school, and far before that, people essentially believed that this is a big simplification, but basically that you have two classes of systems, right? You have integrable systems. So when I'm talking about systems, I mean systems with many particles in it. If you write down a sufficiently simple enough system, sometimes I can make analytical progress. And when we write down those systems, we typically call them integrable. Now, integrable systems will have very special properties. For example, when integrable systems thermalize, when they go from out of equilibrium and then they go through the process of equilibration, um, if you look at their subsystems, they're not described by the eigenstate thermalization hypothesis. And in particular, the eigenstate thermalization hypothesis makes very bold claims about how big the subsystem can be. It's like I can split the system in half, and then both halves will be described by statistical mechanics. Now, integrable models instead will have to be well, they can thermalize systems, their subsystems, but it has to be a very very small piece of their subsystem. It's almost like the dynamics aren't powerful enough to make the description of statistical mechanics something that's like macroscopic, let's say. Um, and so we can do that, and so those systems are also not they're not quantum chaotic. They're not described by this Wigner surmise. They don't have these same statistics. Instead, sometimes they'll have something that might be familiar is Poisson statistics, right? It's like instead of the Wigner surmise is defined by level repulsion, basically. Like the energies don't want to be close to each other. They don't want the gaps in the energies to go to zero. So in general, you get non-degenerate energies in these types of systems. Every energy is unique on average, right? These are statistical claims. And in integrable models, instead you have level attraction, where the gaps in the spectrum heavily peak at zero. Um, and so these systems and other integrable systems basically have a delta function at zero, where like the gap is basically almost always zero. So these systems behave very much differently from what we call non-integrable systems. And non-integrable systems typically find themselves being described by random matrix theory. They satisfy the eigenstate thermalization hypothesis. And they have all of these wonderful like attributes that we can't possibly explain from a more microscopic, rigorous mathematical description. We're basically left to our own devices, simulating them with numerics. Now, interestingly, like in the last like let's say 6 years or so, what's called a minimal model for quantum chaos was discovered, and it was rigorously proved to be quantum chaotic. And these are models that I work on now. They're called dual unitary models. Now, we have to go a little bit outside of the original setting where I was talking about, where you just have a closed system and then it evolves with some type of Hamiltonian dynamics. Basically, dual unitary circuits can be described, or dual unitary models can be described in two different settings that are both equally interesting. One would be having a system that is periodically driven. So I pulse like a magnetic field into the system to drive to drive the system in some way, and I do that in a periodic manner. This is called like a Floquet model. Um, and an alternative way is that you can just say, okay, well, these quantum computers that they're describing, they're physical systems, and I can just describe a specific type of dynamics on a quantum state with quantum gates from a quantum computer. And basically, the idea is that these dual unitary gates are they're unitary matrices, right? That have this property that they conserve probability when you apply them to a quantum state. Now, the very strange statement that I'm going to make is that these dual unitary matrices, they have a dual property in them. And what's that dual property is that they conserve the probability of quantum states. They're unitary when you apply them in the time direction. However, they're also unitary in the space direction. Okay, that's a weird thing to say. How could we even picture that? But the idea is that dual unitary matrices couple two qubits together at a time, and then you build an evolution um, in sort of like this. Maybe you could imagine something like a brickwork pattern of these matrices. They couple two qubits, and I make a row of them, right? So if I have an array of qubits and I label them from 0 to n minus 1 or something like that. Now, you can imagine I have an array of dual unitary matrices that couple for the even to odd qubits, so 0 and 1, 2 and 3, etc. And I make an array of that. And then on top of that, I then make another array, and instead of coupling the evens to the odds, I couple the odds to the evens. So I do 1 to 2. And if I keep doing that pattern, you get a description that couples all of the qubits together if I go far enough in time, right? So this is how you see lots of quantum circuits and quantum algorithms that look like this. Now, the thing is that like that type of description, if I just take the circuit, right? I stop thinking about the state and I just take the circuit of all of these dual unitary matrices that are coupling to each other. The thing is that I could think about trying to contract them together sideways. Like I don't need to go bottom up in time. I could think about contracting things left and right. In general, what happens when I have a unitary matrix that's like that? Um, the the left to right property is not unitary. It's something else. It's like it's like a mess. But dual unitaries are a general class of matrices that have this property that when I change my perspective and I look at the diagram from a different direction, they're still unitary matrices. And it sounds crazy, but somehow when you demand that property from these matrices, they become basically maximally chaotic. So much so that it's almost like I went from the non-integrable description where things are not chaotic, and then in the middle I have the normal chaos, and then all the way to the extreme you have dual unitary matrices where I can make analytical progress like they are integrable, but now I've overfitted in the sense that these things are now way more chaotic than other systems. So, for example, you can make statements like, when I said quantum system, like when I time evolve a quantum system, it maximizes the entropy, uh, like on the subsystem. Well, dual unitary models do that maximally fast. You can't do it faster um, than these models. Another thing is that like one thing that we like to do when we study quantum chaos is we like to look at something called the spectral form factor that tells you something about the equivalence between the dynamics of a quantum system and a random matrix sort of theory. And the idea is that typically what you observe is the random matrix theory. When you study the spectral form factor, it's just a ramp, it's just a line. Um, like and the coefficient out front tells you something about the physics that you're observing. Now, if you then look at a real physical system, there's something called the Thales time, and the Thales time tells you that um, the quantum system will start in a it will start in a sort of a dynamical regime that's quote unquote not universal because it doesn't agree with the random matrix theory prediction for what the dynamics should look like. But if you wait long enough, if you wait till the Thales time, all of a sudden you'll start to see the dynamics look like the ramp. And as soon as you see that ramp, okay, so that this system is quantum chaotic. I see the ramp; it agrees with random matrix theory. And here's the thing about dual unitary matrices: the Thales time is 0. So so immediately these models are quantum chaotic, and so this is why we call them maximally chaotic. And so they are in physics like a certain philosophy that you can take while studying many body physics is that you want a minimal model for, and when I say the minimal model, I mean the simplest thing that you can write down that reproduces the physics that you care about, and then that tells you that you know like a Hamiltonian that looks like that will have this type of physics, and then you can then look, if I change this behavior, do I maintain it, whatever. And the idea is sort of like this concept of universality classes. And so, to everyone's sort of shock, or at least to my shock, someone found a minimal model for quantum chaos and sort of like threw a wrench in this sort of idea that the types of physics that I care about or that I'm interested in can't be described analytically. Now, it comes at the cost of sort of like this overfittedness of the fact that technically there's properties of this model that that aren't that aren't normal, in the idea that it's like, the Thales time is zero. Everything it does is it's sort of like maximally, sort of good at, like every property that we expect to find in the model. It also comes with a statement of like, well, actually, this is the fastest any model could do this, or something like this. So it's a very extreme example, but it throws a wrench in this notion that, I mean, a couple of years ago, I would have told you that there's probably no hope to prove the eigenstate thermalization hypothesis is true for a general class of models. But I guess my understanding and the community's understanding, especially with the existence of these dual unitary models, is that, I mean, maybe there is hope that will make a lot more progress than was initially thought, or at least that I initially thought.
Mhm. Two different kind of questions that suddenly just arise from this entire description of yours. First being a very first principles kind of a position. These isolated quantum systems, which are governed by unitary dynamics, they seem to be reaching equilibrium, right?
Yes.
But inherently, the unitary evolution of the said quantum systems, they are deterministic and intrinsically do not reach a
Yeah, they do not.
thermalized state. So how does that work?
Yeah, so it's an interesting thing, and I actually have some work in the literature on this. So the idea is the following. Of course, the global state will never be in equilibrium. The global state will always evolve, as you say. Unitary dynamics, especially with a pure state, you're never going to go to an equilibrium description. There's always going to be dynamics. There's always going to be things moving. But the like basically what's going to happen though is that, as an experimentalist, if I'm looking at this system, I'm not looking at the global system. I have to sort of like, I can't be that like ambitious. That's just too much information. If I have a material, there's like an uncountable amount of things that I could track. So realistically, what I'm going to do is I'm going to track a couple quantities, and so like let's be real simple here, and like let's track the polarization of a spin, um, in an electron, or something like that. So I'm going to ask like if I'm going to ask specifically sort of a quantum mechanical thing about spin. I'm going to ask specifically in the z direction. What's the expectation value from my experiments? Like, what's the average that I observe this spin orientation, right? Like, I'm going to ask a very simple question. And now, if you look at that from the microcanonical description, what happens is the following, right? So the system starts out of equilibrium, and then you see lots of dynamics. Like, things are very much moving. Um, but that spin orientation will eventually relax to the description of statistical mechanics, and what's sort of what's microscopically happening is like is basically like is sort of like a dephasing thing. Like the configuration of, like, really what you're doing is you're tracking a big sum of complex numbers, and you're summing all of them up, and you're getting a number, and that number is the expectation value that you'll see in experiments. And what's happening is that at t is equal to zero, at out of equilibrium, the configuration of all these complex numbers is kind of weird. It's a very particular distribution. And as I let the system evolve, eventually these complex numbers like basically form a cloud, like a uniform cloud around the equilibrium point. Um, and essentially that average ends up being the statistical mechanics average, and the time it takes for this cloud to go from a atypical configuration to a, like, let's call it a typical configuration, in the sense that the cloud always basically looks the same, even though it's changing, it still looks the same. Um, like that's what we call the thermalization time or the equilibration time. Now, like we can dig a little bit deeper and tie this back into ETH. Like the question is why, like there are cases called quantum scars where like this cloud really isn't so much of a cloud. There's actually only like a couple points, and surprisingly, even though I have a lot of even though I have like a lot of like bodies in my system, I can have something called quantum scars, where there will be states in the system that don't look typical. They don't satisfy the eigenstate thermalization hypothesis, and I can accidentally start my system in a way where it heavily excites these states and not the states that are typical. Right, so that's a way for you to not arrive at equilibrium, and then dynamics will just continue. Right, so the story of the emergence of statistical mechanics, um like it's not guaranteed. There are many ways to not get it, but these ways are, um in a sense, you have to look for them. Like typically this description of going to statistical mechanics is what you find. uh and yeah, and so that's the idea. But okay, so what's happening? Why if I take like the eigenstate thermalization hypothesis at face value, and I ask myself, why are there so many points? Well, what are these points? We have to go back to describing the evolution of the system with the energies, basically the allowed energies. And when I take my initial condition, um and I try to describe my initial state with respect to the acceptable energies, or the energies that it takes to describe my initial state. What I find is that there are like an incredible amount of like, let's say, um, configurations of the system that are excited or you need to describe the initial state and all of its dynamics. And that's why this cloud is so dense. And once it starts revolving around the equilibrium point, after some time, that's why you sort of get to a point where the cloud is changing, but you can't see it with your eyes. Like it's just what's happening, right? And the reason why you get so much, this is sort of getting into like the math of it, but basically the interesting thing is eigenstate thermalization hypothesis is basically a generalization of random matrix theory. Okay, this is a weird statement in the sense that, um, if you take a random matrix, it doesn't really have a notion of like energy or temperature or anything like that, in a sense, right? Like um, and so if you put like, and if you try to use that description from quantum chaos and try to recover something that looks like statistical mechanics, you just can't, because there's no notion of energy, temperature, etc. So eigenstate thermalization basically says no, random matrix theory describes specific portions of the spectrum, but the global picture is more general than that. And that turns out to be true. But basically, what you get then is that, if I start out with a very particular initial state that I can think up, that's easy for me as a human to think about, and then I compare which energy configurations I need to then describe that initial state. Well, all of the energy configurations are basically random vectors, right? And so if I try to say how much weight does my initial condition have on this energy configuration, well, the answer is basically like there's exponentially many energy configurations that it fits into, and this is sort of a consequence of quantum chaos and the eigenstate thermalization hypothesis, that the eigenstates themselves um, are very, very random. So initial conditions tend to excite a lot of energy configurations that are in a specific energy window. Okay. And what you can then do then is basically say, okay, so I have a lot of energy eigenstates. This cloud has the potential to be that distribution that I said, where it's circling around, the equilibrium point, and eventually I can't tell that it's changing. Um, can I prove that mathematically somehow? and the answer is yes, actually. So this is something that we have made really good analytical progress on. There's earlier work, but one of the final works of my PhD also contributes to this conversation. And basically, the idea is that all you need for this equilibrium picture, when I track a specific property of the system, like an observable of the system, not the global system, but an observable of the system, uh, all I need is that a lot of these energy configurations are excited. Basically, that's all I need. Um, this property is called the effective dimension of the dynamics, because the state is going to have it's going to have an energy, and it's going to have some variance in the energy, basically, right? But it's not going to have significant weight on energy configurations that are very far away from it, in energy. And but the idea is, so then the idea is that there's some type of effective dimension to the dynamics, and I don't need as many configurations to describe the state. But as long as I have a lot of states going into the effective dynamics, I'll go to this equilibrium robustly. Basically, like it's a proven statement. It's kind of unsatisfying, like the ergodic hypothesis, like we talked about, in the sense that I have to do an infinite time average, um, to do that, right? Physically, you can't really do an infinite time average. Really, what we mean is I'm taking a long enough time window for my analytics to work. So it might as well be infinity. So it has the exact same problem as the ergodic hypothesis, but at least from the perspective of, we actually have an analytical proof that systems will go to equilibrium, and the variance around equilibrium will be exponentially small. Like, you won't be able to see that the system's not in equilibrium, even though there will be a little bit of wiggling, right? Uh, there's always this problem of, really, when I talk about statistical mechanics and thermodynamics, there's what's called the elephant in the room, is I want to be in the thermodynamic limit. I want to have an infinite number of particles. Um, so there will always be a little bit of wiggling in real life, but it will be so exponentially suppressed that it would be impossible to detect it. And that's the statement that we can make, and we can't make any finite time statements, unfortunately. That's another thing that escapes physicists right now, is we can't make robust finite time statements about a lot of things that we would like to.
You also very briefly mentioned about entanglement, and
Yeah.
my question is, primarily, h- how does the rapid generation of entanglement leads to a chaotic evolution, or the evolution of chaos in regards to information?
Yeah, so there's a lot to
Mm.
there's a lot to, like, um unpack here. So there's a lot that I could say. So first of all, I would basically I would state it like the following: a quantum chaotic Hamiltonian rapidly generates entanglement on its subsystems. And that description is that observation is basically the reason why we get like the statistical mechanical description of the subsystems. Now, another thing that happens is called information scrambling. So if I was to set up a very simple initial condition, you know, sorry to bring up what we spoke about before the before the podcast started, but you talked about, like, irreversibility and things like and things like that. And so the idea about unitary dynamics is that dynamics are fundamentally reversible. So how do I see reversibility in physics, even if, like, that's what seems to be true, sort of like macroscopically, right? Like the microscopic laws of nature are irreversible, or sorry, are reversible, right? And so one way to describe this is particularly with what's called information scrambling. And the idea is that, like, okay, so I start with an initial condition, and I know everything about my global state at the initial condition, right? So if I'm thinking about qubits, I know the like each configuration of the qubits, right? Now, quantum chaotic systems will do something, and I guess, like, I'm not a black hole physicist, but black holes are known basically as maximal scramblers. Okay, so they do this process maximally fast, and the idea is the following. Um, when I do the dynamics, um, the information can start out being, like, very local, something very very familiar with me, and if I want to understand you know the quantum state on, let's say, the first qubit, I don't really need to ask questions about all of the other qubits in the system. Now, a quantum chaotic Hamiltonian, though, will will basically scramble the information, so that information that starts out in the first qubit will then get leaked into the second qubit, and then leaked into the third qubit, and so on, and it will start to smear out the information over the whole system. And so you don't get something that is irreversible, in the sense that if I was persistent enough, I could go through and measure the properties, all of the properties of all of the qubits in a very, very, very rigorous way, right? But this would take me essentially forever. It become basically, the idea is that even though the dynamics are reversible, it becomes exponentially hard to measure the system at a specific time, and then to make statements about the past, like where the system came from, right? So it's basically like an exponentially hard problem. It's a problem that, I mean, no one's ever going to overcome, but mathematically you could overcome this. But the idea is that reversible dynamics can generate things that look, for all intents and purposes, irreversible. And this is a consequence of, quote unquote, quantum scrambling, and it's a property of quantum chaotic systems.
Mhm. How exactly do you diagnose chaos, and what are the ways, or more so the metrics, that physicists utilize to observe and measure the scrambling of information?
Yeah, so this is like, it's interesting because all of these ideas are really tied together. So okay, so how do you diagnose chaos? Well, you diagnose chaos by looking at quantum chaos specifically. You diagnose quantum chaos specifically by looking for properties of the system that are similar to the predictions of random matrix theory. So average properties of random matrices. So, as I mentioned previously, you could look at the distribution of eigenvalues, and in particular the gaps of the eigenvalues. Now, what I said, though, is like a little bit misleading, because the problem with that is that that test can actually be misleading. Um, and so what we found, for example, and this kind of goes more towards the integrable side when you see Poisson statistics, is that sometimes you can accidentally find statistics either as finite size effects. Like a really good example of this would be, for example, if I had a quantum chaotic system, but it had a symmetry in the system, then what symmetries do is they typically create copies of the same energy, right? It makes the Hamiltonian just a little bit degenerate. And interestingly, because you have that property, if you take the whole system at face value, um, and I get all of the energy eigenvalues, and then I try to do this distribution, I get something that is not quantum chaotic. Maybe it's Poisson, or maybe it's something that looks even worse than Poisson. It's not the Wigner surmise. It's not quantum chaotic. The problem is that, as I've said, is the in a chaotic system, you you essentially have level repulsion, right? The energies don't want to be next to each other, and this symmetry has artificially inserted something where the energies are not only close to each other, but they're identical to each other in some cases. So what you have to do is you have to resolve that symmetry. Now, the other thing too is that, and once you resolve that symmetry, you get the correct description. So these things can be a little bit tricky. The other thing, though, is that is that these local probes in general can be tricky, and they can give you the wrong statistics or the wrong impression of the model. And so what we've learned probably in the last, like, let's say it's 2025 already. I'm thinking about papers from 2019 and thinking it was 2 years ago, but probably in the last like 6 years, 5 years or so, maybe a little bit back, I think a popular opinion, at least today, is that probably the most robust probe of quantum chaos is what's called the spectral form factor that I mentioned previously, and that's because one, it's a dynamical quantity, and we care about dynamics for chaos. But two, it's what's called a global probe of the spectrum. When I look at the gaps in the energy, I call those we can call those local probes, in the sense that you're really only comparing two energies together, and like that's insufficient um, to talk about dynamics. Dynamics has you really need to talk about and compare all of the energies to all of the other energies, and so the spectral form factor does this, and it sort of robustly probes whether or not a system is quantum chaotic. Now, for scrambling, the interesting thing is that originally it was proposed as a probe of quantum chaos, because if you look at the equations, so basically what people proposed was that um, you could basically diagnose chaos and whether or not the system is in one of these non-chaotic regimes. Like, for example, there's things like, integral models have different descriptions, like in different properties. For example, like a really famous one that is hotly debated right now is called many body localization, and that one is not quantum chaotic. It looks it looks integrable, but we're not sure if there's a lot of open questions around whether or not the many body localization is a true quantum phase of or is a true phase of matter. But basically, what people propose is this thing called an out of time ordered correlator to probe chaos dynamically in a way that's a lot more familiar than just looking at the energy eigenvalues. Because although I can sound very confident when I say that looking at the energy eigenvalues is like a very sort of satisfying and robust way to ask questions about quantum chaos, in some sense, like, it's not, because when we're having all these conversations about the emergence of statistical mechanics, what we care about tracking actual properties of the system that I can measure in an experiment. Um, I can't measure energy eigenvalues in an experiment, right? Like, that's just not physically possible. And so OTOCs basically say, I'm going to quantify scrambling. And originally we basically thought that scrambling and chaos are basically the same thing. Uh, and what we're going to do is we're going to do something that looks like that original classical Lyapunov exponent problem. Now, the Lyapunov exponent is an average statement, in the sense that I just take, I take the distance of the things, and things exponentially diverge. And from a quantum mechanical perspective, that's an average, because I'm like, if it's their positions that are exponentially diverging, I would have to take their average positions, right? Now, OTOCs basically say, let's construct things that are identical to that, um, but instead, I'm going to take the variance on those quantities, basically. So I'm going to take the square rather than taking the not taking the square. From a classical perspective, these things are equivalent. From a quantum mechanical perspective, these things are very, very, very different. And what you find something that looks suspiciously like a Lyapunov exponent description when I take the square of, like, these properties. I take an observable A and I take an observable B, and I take their distance in time. There's some caveats in the fact that I'm going to keep one of the observables fixed in time, and I might vary it in space, and then I take another observable and I time evolve it. But the idea is that basically this thing of information becoming non-local, it perfectly captures that, in the sense that if I keep one of the observables fixed in time, then it's going to remain itself from like the initial condition perspective. And then if I evolve another observable in time, what you find from the equations of motion is that if this observable was initially like, an observable like on a subsystem of the total system that you're trying to describe, to continue to describe it in time, it picks up weight like everywhere in the system. So it sort of scrambles the information from the like almost by definition. And interestingly, these curves for generic systems, like if you track the out of time ordered correlator, they grow exponentially, like a Lyapunov exponent, and we call the community calls these quantum Lyapunov exponents. And so that's basically how you probe scrambling. Now the a thing that I think is mostly resolved, but there's probably still some research to be done, is how much do these out of time ordered correlators actually tell you about chaos? Like, is scrambling related to chaos? And at least from the perspective of the quantum Lyapunov exponents, I would say the answer is mostly no, because you can find this type of growth in quantum chaotic regimes, and then you can find it in non-quantum chaotic regimes. So you find it in, for example, integrable models will have a quantum Lyapunov exponent description, and so on. So this out of time ordered correlator, initially it drew a lot of attention as a local probe of chaos that was dynamical and maybe more akin to what we were used to studying for statistical mechanics. But in fact, it's not. It's not the probe that we thought it would be. There's proposals, for example, specifically studying the late time like fluctuations or dynamics and things like this, that say that these things can tell you like very robust things about chaos, but at least the hype is centered around the Lyapunov exponent description, right? Because that's what chaos is all about classically, and unfortunately, this didn't end up being true.
Another one of the questions is, does the progression of time in quantum mechanics mirror our classical experience of from past to future and the increase in entropy, etc.?
Yeah, it's sort of like yes, the I guess it's hard to answer this question in any other way than yes, in the sense that I guess you'd probably have to dig deeper on interpretations of quantum mechanics. People have tried to quantize time, for example, but for all intents and purposes, our current understanding, or my current understanding of physics, is that the t that you see in the equations of quantum mechanics, we don't really have a reason to believe that it's any different than the t that you see in Newton's laws of motion. But there's also no reason to believe that. I mean, this is the issue of being at the edge of at the edge of science, right? Is that currently we have the stories that we tell ourselves, right? So where I'm basically going to this is basically is probably best described by like the story of how humans have thought about gravity, right? In the sense of like I'm sure in Newton's time or after Newton's time, the description of gravity seemed extremely convincing, right? Gravity's a force. It's well defined by the interaction, mass one times mass two divided by r squared, and you get a constant there. And it's described by Newton's laws of motion, right? And you have these force like these force vectors, and it's a very satisfying description. It's just and for a long time, like that's the story that humanity told itself about what gravity is and why the stars and the bodies in the sky move the way that they did, right? But the thing is that Einstein came around and gave us general relativity, and now the story that we tell ourselves about the description of reality is fundamentally um, different, and so um, now we tell ourselves that Einstein's description of general relativity is that you have is that matter bends spacetime, right? And then the matter moves like on these curves in space time. This is a completely different description that we tell ourselves in human language about what's actually happening. But interestingly, of course, what has to happen is that Einstein's description, if you take the correct limit, those equations that he wrote down have to give you Newtonian physics, right? So in the limit of small mass or whatever it is, and small speeds, you get Newtonian dynamics. So what I can say is currently the story we tell ourselves, or the story that I tell myself as a physicist, is that those times and those different equations are the same. And if we ever disrupt our understanding of time, um, and it's yeah, in some sense, when we talk about this, this irreversibility versus reversibility, in some sense, maybe this is like a tiny, uh, we're getting a better understanding of why things look irreversible when the equations of motion tell us that they're not. If we ever do disrupt our understanding of time, all I can basically say is that in some limit we'll recover the current physics that we're studying right now. Like maybe time is discrete. Maybe time isn't continuous. I mean, in some sense, like we've quantized a lot of other things like energy. So maybe time is discrete. Maybe the universe evolves in discrete time steps. I have no idea, but those time steps are going to be extremely small. Yeah.
Okay, another aspect that suddenly hit me, and it's more of a thought experiment kind of a thing. Not entropy, but the perception of entropy. Does it vary? Has it varied with the kind of environment, physical environment that our society has materialized into? And I'll explain it to you a little bit. uh, we were just talking, and you very minutely touched upon how it feels like 2019 was 2 3 years ago, and it's actually been almost 6 years now, right? It's the sixth year going on. Due to the advent of internet and the interconnectedness of the world to a enormous gigantic extent, has the perception of an individual in regard to the randomness of things and the sheer magnitude of things going on around in their world becomes significantly vast relative to 10, 20, 30 years before, where, as from an individual's perspective, their worldview was limited, direct worldview was limited to maybe their physical surroundings, and hence the perception of entropy and number of variables in their life.
Yeah, I think you can sort of draw this conversation. Sort of anecdotally, a conversation that's going on in academia is like what's changing about students, right? So, um, over time, I would say that education systems have gotten a little bit easier, but I guess so what's really like from an education standpoint and from like a concentration standpoint from a human being's perspective is that we've gone from we've gone from maybe the newspaper is your best source of information, and the radio, and like very very slow traveling news, and very few voices in your head outside of your local community, and the way you interact with your local community was typically in person. You had much more personal relationships with people. um, and now I can boot up TikTok, and I can see within a span of I don't know 10 minutes I can see the content and opinions and things from 100 different people, 1,000 different people, very 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 quickly. Entertainment is so on demand and so easy. Um, and originally after COVID, there was a really big concern that people were going to come into undergraduate degree programs less prepared, right? Because you had people doing online classes. And when you do online classes, I mean, there's no way to enforce that the person should actually be doing the work that they should be doing. And when you have all of these entertainment sources, people have better things to do than doing their math homework when they have Netflix on their computer right beside the thing that they should be doing, right? So there is a huge concern um, about that coming out of COVID. I don't know if they've done a lot of studies on this, but there's also been chatter now that the results of what you saw after COVID, like they're not really going away, right? And there's two explanations. I don't know what the answer is. I don't know if maybe there's studies on this. Is that um, like the education system hasn't really like sorry so the first explanation is that any single person coming into graduate school or undergrad had at some point a huge disruption to their education, so there's gaps there because of the COVID pandemic. But then there's also the issue of the education system hasn't rebounded, and we as a society haven't really adapted to the fact that like children that should be learning and growing and learning how to concentrate have an endless supply of quick and easy um, entertainment. I mean, I like listen, I do it too. I watch TV and scroll on TikTok, right? And that's a thing that I do now that I didn't recently do. A show has to be so fantastic to keep my full attention now. And my concentration has gone down. And people like, I regard myself as like I'm pretty good at concentrating, I would say. And like I'm very susceptible to these things. Another thing is like large language models too, right? It's like not only is entertainment changing so quickly, but people now have easier ways to cheat and be dishonest about what they're doing as well. I've fallen into this trap, right? Like I've been writing code and I've thought, oh, I don't know how to do this. I wonder if Gemini or ChatGPT knows how to would be able to do that. And then you get into this weird cycle of like, well, the code that they generated was super wrong, but it's right in some of the cases. Why don't I just reprompt it and tell it why it's wrong, right? And then you're sitting there for half an hour, and it's like I could have just sat down, wrote down the math property that I cared about on a piece of paper, figured this out in 5 minutes, and coded it up. But instead, I'm sitting here 20 minutes later telling an AI that it's wrong about something that's like super trivial. So the space that human beings have to be that they're in, like it's not clear. Like from an entertainment perspective, TikTok and all these sources are fantastic. There are great scientific like there's great scientific education on TikTok. There's great scientific education on YouTube, like and Netflix, and like all of these things, right? But but like the space to navigate as a person, things are changing so fast that it's hard to know if we're doing the right things, or how to do the right things even to make sure people get the right like education. And with large language models getting more and more prevalent, and how like they're free, you can just boot it up on your computer and they'll do tasks for you. Yeah, I don't really know where we're going. I don't know where we're going. There's sort of like a concern. Like one statement that you could make is that people that are very driven and talented and drawn to science, like they'll just find their way there, and like they'll just be just as strong as previous generations, and they'll have new tools, and that's great. But another thing is that there's lots of people that could make great scientists that are right on the edge, and those people can be tempted. Those people can be tempted either way. Like TikTok is both a great resource to waste your time, and it's also a great resource in some context, depending on your algorithm, to get exposed to science, right? So like all of these things are double-edged swords. Like Copilot can be very helpful for coding, but you can also be tempted to like I'm always really disappointed when I realize someone sent me an email and it was written by like Chat GPT or something like that. It's really easy. Like I don't know if people need to hear this, but it's fairly easy to spot. You shouldn't be. You should be typing your own emails, And for the most part, like Copilot should be Copilot or other coding tools should be basically autocomplete helpers, right? They're very good at simple things and they're terrible at hard things, right? Um, but yeah, it takes discipline, and I'm not sure. Yeah, I'm not sure how things will go, but I'm sure talented people will continue to find the things that they're passionate about, and people will still be doing hard things in the future.
But in general, how does one make themselves prepared for getting into these different these extensively intensive fields of study, which are complex, which may be hard, immensely hard at times, where you'll be just sitting down and just thinking that, full of despair, that okay, I cannot do this. And it's ever more so easier to, at that point, get sucked in by all these other distractions that are just right beside you, sitting there waiting for this moment for you to just leave everything that matters, just because it's hard, and just latch onto them.
It really starts at like a societal level. Like you and I are people that are responsible for this, right? I agree. I agreed to come on the podcast specifically because I think making conversations about science and the things that are actually cool, but like the equations that I talked about are just necessities to have the conversations about the things that are actually interesting, at least to me, right? So making these things accessible is like a first step. It's a continuing battle of society to provide resources for people to get excited about this. No, like you, listen, I'm sure some people are still going back and watching Carl Sagan's content, but really, like the way that content is structured is not fit for like modern consumption. People care now about podcasts, people care about TikToks. I've tried to make TikToks and shorts, and there's great creators on TikTok like Dr. Blitz that are like talking about physics and math all the time, and they have large followings, and I'm sure that there's going to be viewers that are going to turn into physicists because they've watched this content. There's also things like there's like yeah, actually like I've had several people come up to me at conferences and things like that. It's like, oh, I watch your YouTube videos, or there'll be people there'll be people on my channel that say like I help them choose the field that they wanted to go into for physics and stuff like that. Like all of these little things are really important. Like on a bigger scale, media that for lack of better words glorifies science is also important. Like movies. Movies and other and TV shows and things like this are also really important because they cast one of the most important things is to both glorify and communicate the beauty of these things. Um, but another thing is to also make these people like human. Like at every step of my career, I've looked up to a lot of people, and I've thought that lots of imposter syndrome. Can I ever become like that good? But really, it's just for like there's people that are like 3-4 delta away from the masses. But most people that make really big contributions are relatively relatable people that they live their normal lives and they've worked really hard and they've thought really hard about a problem for a long time, and then they make the contribution, right? It's passion and love for a subject before it is I'm like an overly special person and only I could have. This is something that I've talked a lot about like with friends, right? Like it's part of society's problem in storytelling is that they give us what's called like a great person interpretation of stories, right? When I talk about the story of Einstein, you could tell that story just from Einstein, or you can tell that story about how like the evidence was piling up, and he put the last piece of evidence on top of a really big stack, right? And you know what? He is a fantastically smart, or he was a fantastically smart human being, but so is everyone else like in that pile. It does not take like a solo individual genius to give humanity progress. It's actually a gigantic collaborative thing. Most people go unnamed in history, but amongst their peers, everyone knows who is everyone. And and I feel like as you say, like a part of this great person narrative contributes to this issue of people becoming discouraged when things get hard because they think, oh, maybe this isn't for me because everyone else um, has it easy. Like I tend to not really talk about when I'm having a hard time with my peers. I try to talk about it on my YouTube channel to normalize going through a hard time, to normalize imposter syndrome. Like everything's fine. You see I'm doing well, but I've had all of the feelings that you're having. So these things are normal. And I've had people come up to me and they're like, you know, how do you do it? Like you just have your stuff together. Like what's going on? It's like, man, everyone here is stressed out. Everyone here is having a hard time. Everyone here has like these imposter things, and so normalizing all of those feelings is also really is also really important. And then going down another step, it's really teachers. Like I think that if you have a poor math teacher who regurgitates things from a textbook and doesn't dig deep, doesn't give you intuition, um, like that's a huge problem. Like someone's not going to get passionate about math unless they see someone with a passion for math communicate it to them. Like I had troubles in math until I had the right teacher, and then it just clicked. And then from then on, I knew how to teach myself math. But you need that transition, and you need someone. You know, I mean, maybe someone else didn't need that transition, but a lot of people a lot of people do need that transition. So good teachers are really important, and that's another thing that you know this podcast does, and what I try to do on my YouTube channel, and that's specifically things aren't as hard. Like the way things are often communicated in school are way more complicated and way more difficult than they have to be. And that's not to say that we should lower standards. In fact, you should up standards. But the problem is uh, like like an extreme example is for example, in the place that I did graduate school, we did the scientist's first exposure to scientific computing. They had to first boot up onto a Linux server, learn how to navigate that. You know, these are people that probably use Windows machines. I'm sure a lot more people are using tablets now. You know, you can talk to some kids and they don't really understand what a file system is, right? And you're asking them to boot up onto a Linux machine, and on top of that they need to code in C, right? That, as much as I appreciate the goal of that class, right? If you walk out of that class and you've mastered those two things, you're set. Like you're going to find your way in any scientific field, because every field needs computing these days. And if you're really comfortable in Linux and you're really comfortable in C and you can write programs, fantastic, right? Fantastic. The problem is that is not a good exposure for a physics student who's never coded a day in their life before, right? Um, so like things need to be well thought out. Things need to be presented. You know, when I talk about the eigenstate thermalization hypothesis, it sounds really fancy and it sounds really complicated. A third year student can understand all of these concepts if they're communicated cleanly. And yes, there's going to be edge things that are going on in the literature that they can't understand, but that's sort of besides the point, right? And in my opinion, most of physics, most of math, which I can't go beyond that because I'm not an expert elsewhere. Um, Most of those things can be communicated in that way by excellent teachers, and we have a lot of teachers that don't take their jobs seriously. Um, and so, yeah, it's a societal effort to produce talented people that contribute to science from the top down, from the type of media we make to the type of people that are in classrooms. All of these things matter.
I really agree to that. Even and what piles on to this already existing almost unstructured way of communicating such heavy and significant matters is the lack of a very refined and curated curriculum. Because, as you mentioned correctly, I mean, multidisciplinary multidisciplinary opportunities are increasing, but I really feel that multidisciplinary portfolios needs to be a personal choice, right?
Yeah.
But from the perspective of teaching somebody, if I'm teaching somebody, I think it won't be as viable if the degree is of physics and I'm teaching them programming and all these different aspects which they really would not be able to resonate to at the core level.
Yeah.
And I have not really seen very many curriculums which are tailored towards their students and their subject in a very thorough and rigorous manner. Like you see it and you feel, okay, effort has been put into structuring this entire thing. Umpteen times it's like you're studying everything and then it starts funneling down
Yeah.
into something, and it sure works for some people, but it is, I feel, somewhere it's a very ineffective and inefficient process at whole, and things can just be made a little better if more thought is put into it.
Yes. No, no, I agree. And like this is like people need to be able people need to be in a space to find the thing that they're going to be passionate about. Like I came into my undergraduate degree wanting to be an astronomer, right? And now I do condensed matter physics. It's like the opposite end of physics, right? From the very big to the smallest things that you can talk about. And well, sorry, not the smallest things because there's like high energy physics and things like this, but anyways, um and like and for one, I mean, like I don't even know if it would be possible for a high school student, and this is just like a fact of nature, in the sense of you need to be exposed to humanities knowledge like over time. You can't explain to it, like I bought these like statistical physics for babies for my niece, but you know, I'm sure like the details are going to be lost on her, and she's not going to carry that passion into her future. But um you need to be exposed to things like at the appropriate time, and you need to be in a space in such a way that once you do find that thing and it just clicks, you need to be able to transition to that. So I was really lucky that the university that I went to had, I don't know if it still has this actually, but it had an applied math program that had a theoretical physics double major. And what that meant was I got a really big exposure to applied mathematics, and I got to take every physics course that I wanted to, and I slowly drifted towards quantum mechanics, and then thermodynamics really piqued my interest. And then you ask the question, how do you mix those two? Quantum statistical mechanics, right? And like that's the end of that's the end of the story. But a lot of places and a lot of universities don't have the resources. In fact, the university I went to closed the applied math program, and it got absorbed into the math program. And like the moment that you know things get more bureaucracy and more things shoved into one thing, all of a sudden you're getting these things where things aren't really curated for the students' interest. All of a sudden there's a math degree, and then maybe you can mix that with a physics degree. But now the physics degree is a general physics degree, and you have a general math degree, and then all of a sudden you can't do what I did, right? Um, and and so a lot of places don't have the resources. Like you see a lot of things are rebounding, but a lot, for example, a lot of funding for universities hasn't really changed. Like for example, postdoc salaries haven't changed in a lot of places since like the early 2000s. um, you know, a lot of a lot of funding, like a lot of universities lack the funding to create the spaces that we need for people to find the passions that they'll end up excelling at, and instead they create these funnels, and then you just hope that you produce the right type of people. Most I was like my story is like a very special story. So if you're an undergraduate student and you think, you know, by second or third year I need to know what I like here's the problem. Most of my peers came into their masters or PhD not really knowing if this was the right field for them, because like I had peers that applied to condensed matter programs and high energy programs, and they were just going to take whatever opportunity seemed the best between the supervisor, and the type of projects that they were that they were offered. For all intents and purposes, they hadn't found the thing that they were really passionate about yet, because most people go through these funneling programs, and you don't get to actually explore um, per se. Like a part of this problem is, for one, you can only offer classes at a university that you have the expertise to offer, right? Like if you're going to offer a black hole physics course, you should not have a condensed matter physicist teach that class, right? They probably could teach that class. I could read a black hole physics textbook and probably regurgitate it to a bunch of undergraduate students. Um, but I'm not going to be the teacher that inspires them to care about about these problems. And so there's only so much you can do when you have even when you think about the range of the questions humanity is asking. Even having 30 physics professors in a department isn't really enough to create a space for people to really get the real exposure to all of the fields that they could possibly get involved with. It's a very challenging problem in an era where a lot of governments are worried about budgets, and there's clawbacks on research funding for some fields but not other fields. So it's a difficult problem. Like, as an educator, you really want to create spaces for people to find their passion, because the moment you're passionate about something, you're like 10 times better at it, right? Um, but it's a really difficult problem, and on top of this, you're asking people at universities that have a million other things to do, right? Like, a lot of professors are teaching, like a typical junior professor might be teaching 2 to 3 classes a semester, and those classes might have like 80 students in them. They have to manage the TAs. On top of that, they also have PhD students and master students, and on top of that, they're expected to maintain a like a top of the line research thing. They're attending conferences. These people have a lot going on, and unfortunately, the culture is that you end up like these people also need personal lives. They need to spend time with their family. So where's the first place that they can cut corners? Well, the easiest way to cut a corner in that description then would be, if you stop paying attention to your PhD students and your master students, well, your research program is going to suffer because they're publishing papers with you, right? Going to conferences and stuff like that, you need that to keep your research program going. And so a lot of people end up cutting corners by regurgitating textbooks to undergraduate students. And so, like, the whole system is sort of, it's almost there. Like, you can see that it could be better, um, but currently it's not exactly what it could be.
I think one way for the students to be able to get exposed to these various different subject specific and niche domains that they might not really find at their university amongst the cadre of professors that are available there is through the internet, right?
Agreed.
Social media.
Agreed.
And we were talking about this. And as somebody, if you feel that you yourself are have branched into a domain that is a very niche subject or is something even different than what the masses are doing, I think it becomes starting with the entire process of science communication is an investment that you're putting into the society,
Agreed.
because you might not realize this, but you just sheerly documenting or putting out what you already know or what you are learning yourself might be able to inspire people who are not able to find this specific niche thing that you are doing in their personal surroundings.
Yeah. No, I agree 100%. And, like, I'm a big advocate for, like, a lot of people shy away from scientific communication. And in some sense, like, I have too, in the sense that my YouTube channel, but, like, there's like specializations for this, right? Like, the conversation we've had I think most people could boot this conversation up and appreciate this conversation. My YouTube channel though is really aimed at senior undergraduate students because I want them to understand what's interesting about my field and try to pique their interest. Because these things, I mean, for one, you don't really learn quantum any body physics in undergrad at all, and if you do a condensed matter physics class, you typically do it in fourth year, right? And so, how are you supposed to decide to go like? And by the way, condensed matter physics is by far the biggest field in physics. It is like 40 or 50% of physicists are somehow related to condensed matter physics. One, because it has like actual industry applications. You know, it's very close to material science. Um, but two, I mean, it's just such a diverse such a diverse field, right? The problem is that the education system, rightfully, because you need so much infrastructure to get up to that point, rightfully doesn't really expose you to these topics until like much later. Like you need to describe conductors and insulators and materials. You need quantum mechanics. And to get to quantum mechanics, it does not make sense to not have a good classical mechanics background. um, and all of the math and machinery, this takes time to train people to get to that point. But then the problem is that okay, now you've got the intro. Now what? Am I passionate about this because I just learned about condensed matter physics from like the 1950s? What's actually what's actually going on in research now, right? And so yeah, I agree. I do wish more people did podcasts. I wish more people did YouTube, TikTok. There's great creators on the double edged sword, right? Like there's lots of bad content on YouTube that is potentially damaging to society, but then at the same time, this is also a fantastic platform for scientific communication and to get people involved. So my content is really centered around. And it's a much nicher, smaller audience. Is centered around trying to get undergraduate students or graduate students um, exposure to concepts that might seem intimidating at first, but really they're like everyone has all the machine. You can summarize a lot of really core topics that are really prevalent in research right now in a 20-minute video. If you take someone with a third year understanding of physics, you give them like a five to 10 minutes of context and warm up, or point them to another video that has like 20 minutes of warm up, and then you can get them right into the topic and understand and have them understand, what are the open questions, why is this interesting, how does this relate to the bigger picture. All of those things are possible. Most things are much more simple than they seem. If you follow the path, the correct path up to understanding that thing, a lot of things are way simpler than they seem. The problem is that like how are you going to find that correct path? That correct path has to be laid out by someone who already understands, right? Otherwise, you need to go through the pain that other people did, right? Like for example, a lot of review papers get handed out to graduate students as resources to get into the field. The problem is that as a person who understands what's going on in the field, the review papers are fantastic resources, right? Because you're like, oh yeah, I forgot about that paper, or oh yeah, I didn't quite understand what people were doing for that question, but now I understand because you've summarized it for me. You give that to someone who's brand new to the field, and every single citation and every single statement is going to be completely foreign to them because these are condensed. Like nothing really in the scientific literature is designed to teach people how to get things that's not true. There are some good educational materials for some communities, but really I think like YouTube, podcasts, etc. Like these are fantastic spaces to get people both excited about and even to get them started on thinking about advanced topics.
What then would be your a conducive piece of advice, or multiple, like up to you? What would be your conducive piece of advice for young people?
Um, I mean, for young people, I would just say, okay, so here is the universal advice that I would give to any young person that's already excited about science, and that would be learn programming. And like that's for a lot of people that might not be a fun answer, but the idea is that every single field is getting closer and closer to be for it being a necessity, and every single field you will be a necessity to research programs everywhere, and you can make yourself useful everywhere with programming. If it comes from, for example, data processing, listen, it's easier to set up a Python script than it is to set up an Excel spreadsheet once you get used to it. And once it comes to simulation, listen, when you want to do theory or you want to understand something, there's two types of experiments you can do in reality. One is to go into the lab, and this is a very hard and rigorous process, and it's very expensive. um, the other type of experiment is numerical experiment, and this can be very, very, very revealing about the types of phenomena that that you're interested in. And going back to the conversation, sometimes the thing that you want to do can't be solved analytically, and sometimes it's very inaccessible experimentally. And so the only tool that you could possibly have to investigate a question you're interested in is a numerical experiment, right? So that's the first boring advice. Learn programming. There's lots of here's the steps that I would that I would follow. Is I would learn Python first. There's going to be a lot of chatter, even on my YouTube channel, where I say, well, Python. I use Python every day, but I use it for data processing and data visualization. And then depending on your passions, pick up other skills. Most fields will have specialized or not specialized languages, but languages that the field prefers to do their things in. I write all of my numerical experiments in C++. You don't have to do that. Julia is a popular scientific computing language now. Some people write their scientific computing in Python, and for a lot of workloads and tasks, that's fine, right? But learn Python first, and then as you understand what's going more and more on like in that world, you will know it will be obvious to you what the next steps will be. So just get started on that. For another piece of advice is like just as long as it is accessible to you, explore your passions and be curious. Like a lot of people will find themselves in situations where that's not viable. If you find yourself in a situation where you have the freedom, and you need to think about this too, right? Because a lot of people have anxiety and things like this. Um, if you like, you should, if you find yourself in a situation where you are allowed to be curious and ambitious with your life, then take advantage of that. I think probably the best resource on earth right now is YouTube, and that is when you see a scientific creator. If you watch their videos, or an engineering creator, or whatever you're interested in, there are people in that space almost surely. Like if you're interested in the space, there are almost surely people in that space making content at various levels of difficulty. So for software engineering, for example, you're going to find people that are giving very basic introductions to tasks, and then you will also find people that will write video games from scratch in C, right? You can learn everything about software engineering on YouTube if you're motivated enough. Now, that is not to say that you don't need formal education, because formal education is really important to get scope, but to get specialization and to get exposure to become passionate about things, the really important thing is exposure. Like you just need to, yeah. So I would just say be curious and use the resources that you that you have. Like a question pops up into your mind, there's probably a good YouTube video or a Wikipedia article about that. So just be curious and explore your passions.
Hmm. One thing that I loved about this description about your that you gave is, and something that clicked. People, what people do is they perform an inverse understanding of this the importance of formal education. They rely on formal education to spoon feed them, and when they realize that that is not the case, that is not what's happening, they they delegitimize the significance of it in the first place.
Yeah.
However, it should be the other way around. feeding your interest should be your own personal responsibility. Formal education, your degree, it is supposed to be a platform for you to put it out and test it out and be able to just find other people in that domain or domains ancillary to it, to just be able to again just go steps higher and higher in any particular regard.
Yes, and it also forces you to see breadth, right? Like, so this often comes up when people ask me, how do I get involved in scientific computing? How do I learn this? Like, for physics students, like one of the issues that you have in the education system is that you actually don't get breadth from the education system. Um, from the standard physics curriculum, basically. So what happens so physics is a very computational science these days. Most people write code to do to do science. Now the problem is that undergraduate educations. I actually did a post a poll on this on LinkedIn, and one thing that you can conclude is that most people see like at most two classes of coding in their physics degree. Now the thing is that once you get to graduate school, you get sort of exposed for how weak of a background this is. Coding is something that you can do. Like you can get PhDs in computer science, right? Like these things are very difficult. Very difficult fields to get good at, and you see the exposure of, what does it mean to not have the width, right? So one thing that I often recommend people, and it's sort of a half piece of advice, is the best way to get involved in scientific computing is to start, right? So I said, pick up Python and start doing stuff, right? Now the problem is that, like, let's say I pick a project, like I want to do a Monte Carlo study of an Ising model, and I want to see like a phase transition in statistical mechanics or something like this, right? The problem with that is that there's going to be a fixed set of tools and ideas that you need to learn to be able to do that task, and you won't touch any of the other ideas. And so, if done correctly, a proper exposure to scientific computing doesn't just involve solving physics problems with a computer. It also starts talking about things like numerical analysis and understanding what a computer is actually doing underneath the hood to represent numbers, right? If you don't understand that, you will oftentimes run into errors in your program that are unexplainable. And then another thing is, another thing is like computer science, like getting used to like algorithms, and sort of a broader understanding of what the computer is doing with memory, and things like that. Like very like this type of width changes someone from I can do the simulations in my field in an inefficient way to being a person that can tackle new problems very easily. Like it is a very painful process to always have to learn something difficult and new every single time you start a new project, compared to someone who has a very broad scope and like understanding. So it's like every time you see a new concept, it's like, oh, I've seen something like this before. And the thing is that professors that are offering these classes to you are doing it in a way where they're trying to give you all the skills that they think are useful. It's sort of like I was in the applied math program, and then I took an electromagnetism class in third year, right? Now I had already taken a partial differential equation course, and third year electromagnetism is just partial differential equations, right? So for me, this class was, I think I got like a 98 or something like that percent. All of my physics students, all of the people in the physics program that were my peers, um, they weren't forced to take the partial differential equations class, so a lot of them chose not to. And so this was the first time, and it's sort of like you encounter a problem and then you have to learn the tools to solve that problem at the same time. But a more comprehensive education that's offered by universities, for example, will make it so that when you encounter a problem, you almost surely already have the tools to solve it, or you're close to having the tools, right? So sort of like it's sort of like like learning things when you encounter the problem versus learning how to solve a wide range of problems and then encountering problems. And the efficiency of a much broader scope of understanding to solving problems is just like nothing can rival that. Self teaching cannot rival that. You need an institution to properly structure an education for you to get exposure to enough things to have that.
uh, I really agree to all of that, and it's it's really all about being able to find what works for you the best.
Yes.
And since most people just it's hard, it's a hard thing to hold yourself accountable for 4, 5, 6, 7, how many so ever years while pursuing such a complex field of study. And formal education, your entire system of education institution, it facilitates a medium for you to be able to hold yourself accountable in that regard. And coming back to that, it's really just being about to it's just really the matter is entirely about being able to find what your specific sweet spot is in regards to what you can do to
Yep.
contribute in whatsoever way. While and that intrinsically means that what with what set of tools you're able to establish yourself unique amongst a crowd of lookalikes.
Yes. I've always said, there's a lot of people that can be very like idealistic about science in the sense that you should like the only thing that actually matters is how much you care about the topic and the big picture question. But I've also said that like as a counterpoint, I almost think that the most important thing is that you should like and be passionate about the day to day tasks that are relevant to solve the questions that you care about, right? Like if you hate linear algebra, quantum mechanics is not for you, right? If you do not have intuition for linear algebra and you did not enjoy it in undergraduate, it's probably not the right field for you. And if like let's say you don't like coding, well, a very computationally focused field of physics is also um, not for you, right? So like you need to both be passionate about the big picture, because the big picture is going to be the thing that motivates the types of questions you ask and how much you keep up with the literature and uh and like how motivated you are to get up in the morning. But another thing is like if you don't like sitting down and actually working on the problems that you've concocted or the task that you're being given, that's also really going to be an issue for your productivity. So that's another, I guess that's another piece of advice that I would say is pick a path where you enjoy as much of it, as much of all of the aspects of that path like as you can. There, nothing's ever going to feel perfect, but the day-to-day tasks, if you have the luxury of choosing a path that you like the day-to-day tasks, you should choose that path if you can.
Coming towards the culmination of this particular episode, there's this final segment that we do in each and every single one of our episodes. Dr. Riddle, what will be your word to humanity at large?
Um, it's a very let me think about that very briefly. Like I think the word to humanity has to be like a word of like optimism and hope. We have a lot of coming back to the conversations that we've had today. There's a lot of problems going on in today's world. And there's a lot of problems even from like a basic societal level of like how do you deal with like teenagers attention spans and TikTok, and um things can feel like things aren't going like that well. But in reality, I think that there's a lot of cause to be very optimistic about where humanity is going. Right, things can always take a turn for the worse, but things have. It's never been a better time to be a human being than it is now, and there's no reason to believe that that won't be the case again 10 years from now, 20 years from now. There's going to be speed bumps and there's going to be issues, but with everything that's happening in science, and there's lots of positive movements in society. Like we're trending in the right direction, and with the bombardment of news and negativity and all of these things, it's very easy to be pessimistic about where we're going. Um, but I think there's a lot of cause to also be very optimistic and pushing towards the future that we want. And it's kind of like a yeah. Maybe they weren't inspiring words. It wasn't a one-off sentence, but I think that's what I would say.
I think it was perfect. Dr. Jonathan Riddell, thank you so very much for doing
Thanks for having me.
this episode. It was a lovely conversation. And more than just being a lovely conversation, I personally really enjoyed talking to you about all the different matters that we did. And one aspect that I love the most is how we were able to balance the highly theoretical discussion with the more practical and pragmatic facets,
Mm,
which I feel would be even more so beneficial for the viewers, anybody who will be turning in. So
yep.
thank you so very much.
Oh, thank you for having me. It was a good chat.
Okay.